Good afternoon. This is our narrated version of the PowerPoint for Chapter 6, which is all about air pressure and wind. This is a fun chapter. This begins the material for your second exam. The second exam will cover Chapter 6, 7, and 8. What do we see in the background there? Well, we see windmills, of course. I personally hope we will expand on wind power. All right, so what does this phrase mean, in by day and out by night? What they're talking about here are land versus sea breezes. We will discuss those in this chapter, and it's going to have all to do with the differential heating of land versus water and what happens in the daytime versus overnight at the coast. Okay, so what is wind? Okay, well, the underlying cause of wind is the unequal heating of Earth's surface. So we know that, right? What part of the globe gets the most heat? Well, that would be the tropics, of course, between 23.5 degrees north and 23.5 degrees south latitude, and everything in the middle there, including the equator, is heated, a lot, gets a lot of incoming solar radiation, and then much less so at the poles. So what is the definition of wind? It's basically the horizontal movement of air from high pressure to low pressure. That is wind. We know what it feels like. We've all experienced wind, and plenty of us have experienced tropical storm or hurricane winds. So air molecules will always migrate from areas of high pressure to areas of low pressure. So the pressure gradient force determines if the winds are light and breezy or if they are strong. What is the pressure gradient force? Well, that is just describing, how fast a change in pressure do you have over a given distance. So this image here is being described as a blizzard. Okay, so what makes a blizzard? Well, does it necessarily have to still be snowing for it to be blizzarding? And the answer is no. It looks here like perhaps the snow has stopped. But if you have winds whipping that material around, or you can have winds whipping it around as it's falling, if it creates whiteout conditions and reduced visibility, then that's what we refer to as a blizzard. So this is in Great Britain, and we're looking at a seawall here with, of course, a lighthouse perched atop. And we might ask a question, are the winds strong or weak here? And the answer is the winds are strong. Do we see visual evidence for that in this PowerPoint? Yes, we do, because we see the waves very big. Okay, so what produces waves in the ocean? We're not talking tsunami waves, we're just talking regular waves, and that answer is wind. So the actual storm here might be far out to sea, but the winds are coming in regardless because you do have some pressure gradient force here. All right, so this is this is in the UK back in February of 2002. This is some kind of winter storm. So basically you have very strong winds, and you can see kind of in the top right corner there, I guess maybe there's some kind of seawall there, or perhaps that's just part of a boardwalk. Anyway, you see that the waves are very big, and that tells you that the winds are strong. They're pushing waves, they're actually pushing seawater up onto the land. And you see there an electric trolley car. Looks like it's still running, I guess, unless that thing in the back is something that's pushing it along because it's not working. Anyway, typically you don't have the water right there. I personally find it a little terrifying, the thought of anybody being on an electric trolley car in the water. Water and electricity don't really mix safely. Okay, so wind occurs because we have differences in air pressure from place to place. But what is air pressure? Can you see air pressure? Well, no, of course not, because we know that we cannot see the air molecules. They are invisible to us. Can we see the air pressure? No, but can we feel the air pressure? Okay, so we can think of air pressure as the weight of air molecules above us, or also as the density of the air. And do we feel that? Well, no, we really don't. We have evolved to live very nicely in the air pressures that we have on this planet. Our typical air pressure, or the average, at sea level is 14.7 pounds per square inch, and we have evolved to live quite comfortably in that. But, you know, if you ask an older person that has arthritis, and I'm assuming it's got to be the rheumatoid arthritis, I don't know if osteoarthritis, if this also happens, but older folks with rheumatoid arthritis might tell you that they can actually feel low pressure systems moving in. So low pressure systems are going to bring rain. And these people will say that they feel a difference in their joints. And I'm not sure how it works. I want to say I think they feel more pain when a low pressure system is moving in. I could have that backwards. I don't have rheumatoid arthritis. I have osteoarthritis. And it's different. And anyway. So what we're looking at here is just a drawing trying to show that, you know, the weight of the atmosphere above us, the weight of the atmospheric gases above us, that is air pressure. And if they had, well, of course, they're not really showing the troposphere here. I was going to say, if they were showing the thickness of the troposphere, it should be thicker at the equator and less so at the poles. And perhaps they're just showing the entire atmosphere together, all the different layers. Anyway, but let's take a look at that column over there on the right. So, of course, those gray balls are O2 and N2 molecules, and then the other trace gases that are in the atmosphere. So as you look at that, you might, well, you guys tell me, where do we see the air molecules more concentrated? Do you see that they are closer together at the bottom and spread further out at the top? That just tells us something we already know, which is that the density or weight of Earth's atmosphere is going to actually decrease with height in the troposphere. So this is a simple mercury barometer. Now, you're not going to need to know anything about barometers for your exam, but we'll just discuss it briefly. This is an old school barometer. So you have this dish at the bottom that's filled with liquid mercury, which, as I'm sure you know, is poisonous. It's not something you just want to mess around with. And then you have this hollow tube that's connected to it, and it's vacuum sealed, and then you have mercury in the tube, and it can rise or fall. So how this works is if the air pressure is increasing, which is what they're showing here in this drawing, notice those blue arrows pressing down. Let's say we have a high pressure system rolling in, air pressure is increasing. So the weight of the atmosphere is going to push down on the mercury and then make it scoot up higher into the vacuum in that tube. So if the pressure is increasing, then the column rises. Sometimes they refer to this as mercury rising. What does that mean, mercury rising? It means that high pressure is moving in. And of course, the opposite is true. If a low pressure system is moving in, then the pressure decreases and the column of mercury will fall. So this is a more modern barometer. This is an aneroid barometer. So it has a partially evacuated chamber that changes shape due to changes in atmospheric pressure. So as atmospheric pressure increases, it's going to compress, squeeze further together, and as atmospheric pressure decreases, it's going to expand. And that image there on the left just kind of shows you. So not only is it telling you, and this is in, I'm trying to see what units, I think the units on the outside are centimeters of mercury, even though there's no mercury involved in this particular barometer. So not only can you read, and I guess the larger numbers there on the inside are probably in millibars of air pressure. So not only can you get a reading from this machine in a couple different units, but it also is corresponding to stormy, cold front moving in, and a violent thunderstorm, rain, a warm front has moved in. Changing fair weather, high pressure, blue sky, some cumulus clouds, and then very dry. So this is an aneroid barograph, which makes a continuous record, 24 hours a day, of pressure changes. So which part of this is the barometer? Can you guys tell? See those coils that look like they're made of copper? That is the actual barometer. Okay, I'm going to want you to know all three of these here for your second exam. So the average air pressure at sea level, we can express it in three different ways. Either pounds per square inch, PSI, inches of mercury, okay, not centimeters, I think I said centimeters earlier, and millibars. All right, so 14.7 pounds per square inch, that is our average air pressure at sea level. Of course, remember that air pressure is actually changing, changes pretty quickly. We might say it's changing constantly. That's just an average, and again, that's at sea level. We're going to have variations in air pressure from place to place all the time. How about in inches of mercury, using that mercury barometer? 29.92 inches of mercury is the average air pressure at sea level, equivalent to 14.7 pounds per square inch. And then in millibars, remember that 1,000 millibars equals 1 bar of pressure. So the average in millibars is 1013.25. So I will want you to know these for your second exam. And of course, as we mentioned before, air pressure does indeed decrease with altitude. Okay, so this is a neat graph here. So they're showing inches of mercury. If you're wondering, what is that Hg there? Well, that's mercury. That's its symbol on the periodic table of elements. So they're showing in inches of mercury and in millibars. So what they're showing here is your average in millibars. They're slightly above the middle. And then it's giving you some other examples here to compare it to. So a strong mid-latitude cyclone, such as we have moving across the lower 48 states all the time, is a lower air pressure. That makes sense. It's a low pressure system. Look at Hurricane Katrina. So as horrible as Hurricane Katrina was, it wasn't the lowest pressure ever. Hurricane Wilma was lower. Those were in the same year, by the way. Rita I think Rita was that same year, but Rita is not on this graph. It didn't have super low pressure, I guess. And then the lowest, of course, this goes back about 10 years probably, this set of slides, but the lowest recorded sea level pressure back then was Typhoon Tip back in October 1979. I wonder if we have beaten that record. I wouldn't doubt it. I wouldn't be surprised. Okay, so let's go above your average sea level pressure then. So your typical strong high pressure system, or anticyclone, of course, is a high pressure system, so it's a higher number of millibars than the average. Highest recorded sea level pressure in the United States, Miles City, Montana. And you might think, well, that's not at sea level, and you're right, but we'll see in one of these chapters, maybe this one, that they tend to report air pressures and sea level equivalents so that we can really compare them from place to place. Anyway, that was back in 1983. And then the highest recorded sea level pressure for anywhere on the planet, at least 10 years ago, was in Siberia, and that was December of 1968. Very strong anticyclone high pressure system. Okay, I know the answer's already on there, and again, that's because these are the online version of these PowerPoints because, well, there's a lot of reasons for that, including that I teach this online in the summer and we're not ever all together discussing it, and it's also there in case we should move to all online learning in this semester. Who knows? This is fall 2020, by the way. The year that just wouldn't end. So our question, which one of the following would produce the greatest change in atmospheric pressure? Would it be A, the difference between the highest and lowest recorded pressures at any one station on Earth? B, the difference in pressure between the inside and outside of a building? Yeah, probably not going to be that. C, a horizontal airplane flight of 200 miles, horizontal. Yeah, probably not going to be that. D, an overland journey from the center of a high pressure system to the center of a low pressure system. That might be kind of similar to A. Of course, A is taking any one station and saying what was the highest it ever recorded and the lowest it ever recorded. A and D will give you a difference in pressure, but it won't necessarily be huge. Correct answer is E, a balloon ascent from sea level to 3 miles up. You are going to get the largest change in air pressure, and of course that air pressure is going to be dropping as you move on up. All right, so this is just kind of giving you an idea. So we're going from, just in kilometers, yeah, from 0 kilometers sea level going on up beyond 16 kilometers. So maybe about the top of the troposphere, we might say roughly about 7.5 miles for the thickness of the troposphere. So what you're looking at here is as you move on up in altitude, kilometer at a time, you are going to experience less air pressure, indeed. But you're going to, not only do you have the air molecules closer together, you know, at lower elevations and further apart at higher elevations, you might notice that when you first begin, you're going to drop 100 millibars in just 1 kilometer. But as you move on up higher in the troposphere, you might go up 3 kilometers before you drop another 100 millibars of pressure. Basically just illustrating that indeed air pressure decreases with altitude. Fewer and fewer air molecules. Okay, so this table, this is a standard atmosphere table. Height in kilometers, temperature in degrees Celsius, and air pressure. So what they're showing here is the air pressure you expect at various heights in the atmosphere. We're going above the troposphere here. This goes all the way up to 50 kilometers. That's kind of neat. And then over on the far right, it's giving you what would be your average temperature at such a height in degrees Celsius. Okay, so in meteorology and climatology, we are more concerned with horizontal variations in air pressure than vertical. Okay, so we already know that there are changes in air pressure vertically as you go higher up in altitude. But what's really important are the changes in air pressure horizontally. Why? Because that is driving the weather and the winds and bringing us different weather systems that we may or may not have an easy time dealing with. So if we look at that map on the left, down there, moving across Florida, you have a cold front that, as you go over the Gulf, appears to be a warm front, but it's sort of stalled on the eastern half. You have several high pressure systems, also known as anticyclones. You have some low pressure systems there. You have one over Oklahoma, and you have the warm front on the leading edge and the cold front on the trailing edge. But notice that the warm front isn't just a warm front, it's a stalled front. We'll learn about fronts. Yeah, I'm not sure. If it's not in this chapter, then it might be in chapter 7 or chapter 8. Okay, so I might like you to know this for your second exam, but this is pretty simple stuff here. So high pressure is going to give us cooler air, more dense air, sinking air. Therefore, you tend to have clear skies because you're not having any lifting. Not from heat anyway. I mean, you still have lifting if you have a mountain range there. But generally, high pressure is associated with clear skies. So we're talking blue skies with no clouds, blue skies with a few cumulus clouds. Low pressure is associated with clouds and rain. Will rain in the warmer months, potentially snow in the cooler months. All right, so going back to the whole mercury rising or falling thing, when the barometric tendency is falling, meaning the mercury is falling, low pressure is moving in. And what should you expect? You should expect cloud cover, nimbostratus clouds, and rain. When the barometric tendency is rising, or the mercury is rising, high pressure, skies will clear. So, what is an altimeter? So an altimeter is a machine that is reading air pressure, but it's scaled for altitude. It needs to be scaled for altitude, especially the ones being used in airplanes. You can buy handheld altimeters that aren't that expensive if you want to take them with you hiking. And it's kind of neat as you hike higher and higher up in a mountain to see the air pressure falling. It also is cool to look at it and get an idea if you have high or low pressure coming in. And you can even get watches that have altimeters on them. I do not have such a watch. Anyway, so it's important for aircraft. Okay, why? Because aircraft, once you get above 18,000 feet, they're generally flying paths of constant pressure instead of constant altitude. So you want to be using an altimeter that is basically an aneroid barometer, but scaled for altitude. Okay, so what we're looking at here is cold dense air and warm less dense air. All right, a comparison of the density of a column of cold air with a column of warm air. All else being equal, meaning your amount of water vapor or anything else is equal, dense air exerts more pressure than warm, less dense air. So let's take a look at these drawings. Oh, and also air pressure will decline faster with increasing altitude in cold air than in warm air. So on the left you see a high pressure system and you see cold dense air. And what they're showing you there with the surface pressure is just assuming in both of these scenarios that the air pressure at that time on the ground surface is exactly the average, or almost the average. All right, so in the cold air mass, your air molecules tend to be sinking down towards the surface. They're all squeezing together. This is high pressure, which is associated with cold, dense, sinking air. On the right, that air mass is warmer. Remember that warm air rises, like a hot air balloon works. So your air molecules, when I say they're more spread out, they're not quite as dense down there at the surface. And also you will notice that if the air mass is cold, you're going to lose more air pressure faster with an increase in altitude than you will with warm air. Okay, these are important here. All right. Number one, cold air is more dense than warm air. Yes, we have covered that already. You guys know that from other classes or watching Weather Channel. So this next one might be more of a surprise. Dry air is more dense than humid air. Okay, so why is dry air more dense than humid air? So dry air doesn't have much water vapor in it, but humid air does. So water vapor, so if you were to go to the periodic table of elements and you were to look at the atomic masses, atomic weights of nitrogen and oxygen, and then compare that to H2O. Remember that hydrogen is just number one on the periodic table, just one proton. Anyway, it's pretty light. So here's the thing. The more water vapor you squeeze into that air mass is going to be less dense because you're displacing some of the air molecules. So in a dry air mass, you're going to have more nitrogen and oxygen and less H2O. In a humid, moist air mass, you're going to have less nitrogen and oxygen and more H2O. So dry air is more dense than humid air. So now let's combine these two things. Warm, dry air is more dense than warm, moist air. So let's say both air masses are warm, but one is dry and one is dense. Well, the drier one is going to be more dense. And then if we're going to compare a cold, dry air mass, like you might find the Arctic Circle, compared to a warm, humid air mass, like you might find over the Gulf of Mexico, as you guessed it, the cold, dry air is more dense than the warm, humid air. Okay, you can pause this if you want and read through this, and this kind of goes through a little bit of the math, I suppose, and the periodic table of elements, just proving that dry air is more dense than humid air. Okay, so differences in air pressure. So why do we have differences in air pressure from time to time? Differences in air pressure from place to place and time to time, producing wind. And it has everything to do, for the most part, with differences in temperature. So it's mostly differences in temperature between those air masses, as one more warm and one more cool, that are going to lead to differences in air pressure. So let's say that you have a warm air mass in place, but a colder air mass is coming in from the west, attempting to overtake it. Well, the warm air mass is going to be less dense than the cold air mass. So that right there gives you a difference in air pressure across the ground surface, and that is going to cause wind. I was just checking there to see if we had anything to follow up with on the next slide, and we do. Okay, so it's kind of an urban myth, I guess, urban legend, that baseballs fly further at Denver's Coors Field. So Denver is also known as the Mile High City. So a mile is 5,280 feet. So Denver's pretty much close to a mile up. And the air pressure there should be less than at sea level. Oh, by the way, in case we don't get to talk about this in class, if you have ever looked at the directions for fixing pasta, you may have noticed that they might say something about high altitude directions and that you might have to cook the spaghetti longer. You may have also noticed, I noticed this when I was a kid, and I would occasionally make cupcakes for bake sales at school. And if you would read the directions on the box, they would have a high altitude direction. It was a little bit different. And I have to admit, I haven't looked at a cake mix or attempted to make a cake in a very long time, more than a decade. So I don't remember if you had to bake it longer or shorter amount of time. But there can be differences in how you cook things based on high altitude. But back to this Coors Field up in Denver. I have since read that the reason baseballs might occasionally appear to fly further is that they designed the field so that when you hit the baseball, it's going to be going in the direction that you might have any prevailing winds, if you have any winds that evening. Okay, so here's another one. This is not necessarily Denver. I guess this could be anywhere. So the sportscaster says the ball is not going to carry very well in this heavy air skip. Okay, so what do they mean by heavy air? They mean it's very humid, like it feels like a wet blanket around you when you walk outside. Maybe that's Pittsburgh. Who knows? It's some kind of industrial city. I've been to the baseball field at Pittsburgh. It's very nice. It's a lot of fun to go to baseball games there if it's not too hot. Anyway, So is it true that the ball will not carry well in the heavy, moist air? And the answer is, well, no, not really, because remember that humid air is less dense than dry air. So maybe the ball will fly a little bit further on a humid evening. Oh, okay, good. They do have a little something about spaghetti in Denver versus New York City. So which of those cities is known for Italian food? Well, pretty sure that's New York. And now I really want New York pizza. Anyway, so where does it take longer to cook spaghetti? So in Denver, the Mile High City, the water will boil at a lower temperature in Denver than in New York. So it'll boil at less than 212 degrees, but it will take longer to cook the pasta due to that lower boiling point. How much longer? I don't know, a minute or two. You can pause this and take a look at this if you would like to. This is in degrees Celsius. Yeah. All right, so we're going to start looking at isobars. Okay, so isobars are lines that connect points of equal air pressure. So that's what we're looking at on this graphic. Each of those straight lines is an isobar, and they are labeled according to how many millibars of pressure they are. So you want to look at your isobar map and you want to see how close together or spread apart those bars are to get an idea of your pressure gradient force. Okay, so pressure gradient force. Air moves from high pressure to low pressure, we know that. Closely spaced isobars indicate a strong pressure gradient, meaning you have a larger change over a shorter distance and therefore stronger winds, higher wind speeds. Whereas the widely spaced isobars indicate a more weak pressure gradient and lower wind speeds, perhaps just a gentle breeze. Hey, let me ask you this question. Is it ever just not windy at all? Sure. You know, there are times, and you notice it more, I think, when the weather is hot, because you want a breeze and you just can't seem to get one. And you walk outside and just nothing is moving. There's not a leaf on a tree moving, and it just seems a combination perhaps of miserable and perhaps kind of eerie as well. So this, you can pause on this if you want to and take a look at this. And this is a little something about converting pressure measurements to sea level equivalents. Oh, we're going to get to the land and sea breeze. Yeah. And if we have time, we will make a drawing of the land and sea breeze on the board and discuss it more when we're in person together. Okay, so we'll start at the top. This, by the way, is going to show a sea breeze. We'll discuss the land breeze, even though there may not be a drawing for it. So the one at the top, A, before sunrise. Right before sunrise, you may not have much of a breeze. Okay, but after the sun rises, well, you're going to start to heat the troposphere. Okay, so of course, remember terrestrial re-radiation, incoming short wavelength radiation from the sun being absorbed by land and sea surfaces, being spit back out at a longer wavelength, being then captured and reflected by the greenhouse gases warming the air around us. Also, recall the differential heating of land versus water. Remember that land heats up a lot more quickly than water, but will also cool down more quickly than water, and the vice versa of that for the water. The water takes a lot longer to heat up, but will hold on to that heat longer. Okay, so now look in, okay, no, we're still in the middle one there, sorry. So we're still in the middle one there. So basically what's happening, actually let's skip Let's skip the middle one. What they're showing there is the end of the overnight land breeze. Let's just skip that. I do hope we get a chance to do this in class together. If not, I'll make a video lesson and put it in this chapter. Okay, so let's focus now on the one on the bottom. Okay, so daytime at the beach. The land, those sand grains, they're going to heat up fast so that air temperature is warm. Therefore, what is it going to do? It's going to rise. So as air is rising, you're taking air molecules away from there and you get low pressure. Okay, now the ocean is cooler in the daytime. It takes longer to heat up. So you have high pressure over the ocean and low pressure over the land. Your breezes are going to blow from the water to the land. That is just referred to as a sea breeze. Okay, so what this image on the bottom there is showing the larger convection that you get with your sea breeze in the daytime. Okay, so there's a question there at the bottom. What happens then at night? Oh, just a second. Back to the sea breeze. If you've ever spent any time at the beach, you might know that, so you're wearing your flip-flops and you're sitting in your chair or on your towel, and if you're like me, you have an umbrella there. Really, it's better to have an umbrella to help guard against skin cancer, but anyway, you guys are adults, you can make your own decisions. So you want to take a break from grading exams on the beach, and you're gonna go get in that water and swim. So you kick off your flip-flops and you start walking in that sand. Boy, it is hot. It's really hot on the bottom of your feet, so you kind of move quickly to get in that water. You get in that water and it feels nice and cool, okay, because it's cooler than the land. Okay, now we can ask that question on the bottom. What happens at night? So at night, overnight, you know, the land is going to lose heat very quickly, but the water is going to hold on to its heat longer. So imagine those arrows reversed and the L's and the H's reversed, and that would be the land breeze at night. So at night, if you are walking on the beach barefoot, the sand feels nice and cool on your feet. Now you don't mind walking barefoot. And you decide you're going to go put your feet in the water. So you put your feet in the water, and guess what? That water feels warmer than the air around you. So at night, you're going to have the low pressure over the ocean and the high pressure over the land, and this will reverse, and it is called a land breeze. So that's the difference between sea breeze and land breeze. Okay, so this is a type of weather map that is just simply showing air pressure. Of course, it's also showing the low and the high there, but those are, of course, connected to air pressure. So those lines are isobars connecting points of equal air pressure. And they are listed in millibars. So you see on this map, we have a low pressure system there over Chicago. You have lower pressure towards the center, and the pressure increases as you move on out. Now, up in Canada, there towards the west, you have a high pressure system. You'll notice 136 millibars for the high in the center, and then it gets lower as you move on out. And then the funny looking symbols there that look like a stick and a ball and maybe some things like you might see on a hockey stick, those correspond to the table over there on the right. Those are wind speed symbols. If it looks like a bullseye, that's calm. That basically is saying you don't have any wind. Okay, so the different shapes, is it just a stick? How many hockey stick parts does it have? Does it have triangles? Each one of those is going to correspond to a wind speed range, anyway, in miles per hour. And then the direction in which the hockey stick is pointing is showing the wind direction, and winds are named for where they're coming from. Not where they're going, but where they're coming from. What they have left off this map would be the cloud cover and the fronts. I can tell you that if we were going to show this on the smartboard and then draw on it, we'd start at that L and we would put a warm front on the leading edge and a cold front on the trailing edge, and they would both be covered with clouds. And then that high pressure we would just leave alone because you're not expected to get cloud coverage or precipitation with a high pressure system. Oh, speaking of, and they have just done that for us. That is fantastic. All right, so in this case, the low pressure has moved over top of Ohio and West Virginia. So you see there with your isobars, definitely indeed, that's a low pressure system. Of course, it's shown with an L for low. Why is the L red? You might have learned this in a previous class because it's warm air. Why is the H blue? Because it's associated with cooler air. So these low pressure systems, which are also known as mid-latitude cyclones, which we will cover, I think, in Chapter 9, are going to have a warm front on the leading edge and a cold front on the trailing edge. And this is an image from the Weather Channel. And this goes back to September 2010. Golly, almost 10 years ago. All right, September 2nd. Or who knows, that might have been Labor Day back then. So what do we see? We see some highs, we see some lows, we see warm fronts and cold fronts. Don't really see any stalled front. Do you see that purple thing kind of on the eastern edge of the Dakotas? Okay, that purple is an occluded front. We'll learn more about the fronts in a later chapter. And of course, what do you see for your Labor Day weekend down there in the bottom right? Yep, you guessed it. We see a hurricane. So that's the symbol for the hurricane. It's going to rotate counterclockwise here in the northern hemisphere. What I want to point out is that if all they showed there were the isobars and they didn't put the green for precipitation or the hurricane symbol there, we'd still know that that was a hurricane there. Why? Because how closely spaced those isobars are and the fact that they are in a circular pattern. Okay, question here that is not on your exam, but we'll briefly discuss it. If air pressure is lower with increasing altitude, and if air molecules move from high pressure to low pressure, then why did the atmosphere not just rush out to space long ago after it formed? And the answer is something called hydrostatic equilibrium. So this is a balance maintained between the force of gravity holding those air molecules in closer to Earth's surface and the vertical pressure gradient. So it's a balance, so the air does not escape to space. That's an awesome thing. By the way, we might as well mention something here that I like to bring up in the Earth Science class, and this is something I saw on Discovery Channel many years ago. So why does the Earth have a moon? Why is the Earth tilted at 23.5 degrees? Shortly after forming probably a rudimentary core and mantle, very early in Earth's history, like 500 million years old, we were hit with a small planet-sized body, like maybe something the size of Mars. What did that do? It knocked us over roughly 25 or so degrees. It also blasted a lot of material outward from the surface that then was captured in Earth's gravity and accreted to form the moon. So what happened is the moon as big as the planet body that hit us? No, can't be, not likely. Anyway, so not only did we form the moon, but the Earth got a little bit bigger. And these scientists that were speaking on Discovery Channel that day were saying that their hypothesis was that if this had not happened, then Earth would have been smaller and we may have been not big enough to have a strong enough gravitational pull to keep our atmosphere and surface water here after it formed, and then we would not have life on this planet as we know it. So it was a good thing that that impact happened in so many ways. Okay, so you may or may not recognize these people, depending upon your age and or have you ever watched old movies or listened to music from the 60s. So over on the left, of course, are a couple characters from Gone with the Wind, a very contentious movie. Over on the right, that is Bob Dylan, back when he looked really young. Okay, so we do need to write these three things down. Okay, so what controls the magnitude and movement of wind? Okay, so wind exists because Earth is heated unequally and air pressure moves from high pressure, air molecules move from high pressure to low pressure. But what controls the magnitude of the wind? You know, are they fast winds or slow winds, and the movement of wind, like where it's going to go. Okay, so the pressure gradient is important, is where it all starts. Air molecules moving from high pressure to low pressure, and the steeper the gradient, steeper the pressure gradient, you're going to get stronger winds. Now, the Coriolis effect we have not talked about yet, and I can't remember if that's in this chapter or another one. This might end up being another 2-hour PowerPoint, hard to tell. The Coriolis effect has to do with the fact that Earth spins. We know Earth spins, right? That's why we have day and night. So what this means is that in the northern hemisphere, winds are deflected to the right, an apparent deflection to the right. So the Coriolis effect, Earth spinning, does not produce the winds, but it does modify the air flow. In other words, it can affect the direction in which the winds are blowing. What else affects the magnitude and direction of wind? Friction, also known as drag. So surface winds are always going to move slower than winds that are at a higher elevation. Why? At the surface, you have all this topography that the wind blows against, creating friction or drag. And as you go higher up in the troposphere, well, you lose that. You don't have any friction. Okay, so Coriolis effect is in this PowerPoint. So it's fun, and in class, if we have time, we will go to YouTube and look at some neat animations and or experiments that various people have created and put on YouTube to try and explain the Coriolis effect. And this is important. When we get to maybe chapter 7 where we do the global winds, chapter 7 or chapter 8, we will spend an entire class period together, and we'll give you guys a template to draw on of planet Earth and the different parallels from 0, 30 north, 60 north, 90 north, and the same thing in the southern hemisphere. And together we are going to map out the global wind patterns and why it happens. And Coriolis effect is going to be part of it. So, looking at the top, all right, non-rotating Earth. If you fired a rocket from the North Pole and the Earth didn't rotate and you just fired it straight down and you want it to reach the equator, and it's a rocket that can stay in flight that long, it's just going to follow a straight path and it'll hit the equator as you expected it to. So on a non-rotating Earth, the rocket would travel straight to its target. But the Earth does rotate, and it rotates 15 degrees each hour. That's just crazy fast. It doesn't feel like that for us. All right, thus, although the rocket travels in a straight line, the Earth beneath the rocket is actually spinning. So when we plot the path of the rocket on Earth's surface, it follows a curved path that veers to the right of the target. And you might say, wait, that solid red arrow is to the left of the target. No, because you're looking at it from the North Pole looking down south. So you're at the North Pole. You're firing a rocket because you're on Mythbusters or you're just a scientist with some money to spend. You're going to fire that rocket at the North Pole, and you want it to reach that particular target, some little island out there off of South America. If you just fire it in a straight line, you're going to miss where you wanted it to go. It's going to go out there in the Pacific Ocean. Why? Because the Earth, in the hour that it took to get there, has rotated 15 degrees. Yeah, so when you're firing a rocket or you're flying a plane, you have to take these things into account. Okay, so if you really wanted that rocket to hit that target there at 90 degrees longitude, you would have to send it in a curved path. You would have to actually point it over towards the 75-degree line of longitude to get it to land on your intended target of 90 degrees. So this is the Coriolis effect, or the Coriolis force, an apparent deflection of rockets, airplanes, and winds to the right, deflection to the right in the northern hemisphere. So again, let's look at the left side of B or the right side of B. If you are going to be standing there on some sea ice at the North Pole and you're going to fire your rocket and you just fire it straight, then as you're looking down from the North Pole, looking down towards the equator, the rocket has veered to the right. Okay, so this is showing that the Coriolis effect is not equal at all latitudes on the planet. All right, so you might notice, look down there at the equator, no deflection. 20 degrees within the tropics, a small deflection, 40 degrees north, Pittsburgh and Philly, intermediate deflection, and then up there at 60 degrees, getting close to the Arctic Circle, there's a larger deflection. So the Coriolis effect is stronger the further away from the equator you get. So strongest at and near the poles. And it's very weak at the equator. Okay, so yeah, so it's not equal everywhere. By the way, the Coriolis effect has to do with the fact that, or is the cause of the fact that hurricanes and other low pressure systems rotate counterclockwise in the northern hemisphere. So every hurricane out there, and as I narrate this PowerPoint, we have Tropical Storm Laura and Tropical Storm Marco. Might they both become actual hurricane? It could happen. Anyway, right now we have 2 tropical storms that are going to hit the Gulf Coast at the same time. Yeah. Anyway, whoever says there's no such thing as climate change, just slap them or something. Stop hanging out with them at the very least. So this is not a fabulous drawing. I guess it's okay. Anyway, what they're trying to show is that you have 2 college students sitting on either end of a playground merry-go-round. And over there on the left, it's not rotating, and they can throw the ball to each other by just throwing it straight. It's better to see these things animated, so we'll do that in class, and if we end up not having class, then I would tell you to go to YouTube and type in Coriolis effect and just watch all the cool stuff that you can see. It's really neat, especially when they spin that merry-go-round and have a camera overhead. It's just really cool. So over there on the right, now somebody is spinning that merry-go-round, and if the person down there at the bottom attempts to throw the ball to the person across from them, but they just throw it straight, the person across from them is not going to be able to catch it because they're turning and moving away from the ball. But what it looks like to the person standing there filming it is it looks like the ball has curved to the right. It's really cool to see those in action. Okay, so just emphasizing something here that we looked at a couple of slides before. So the stronger the winds, the greater the deflection. So you tend to have stronger winds as you move away from the equator, going either farther to the North Pole or farther to the South Pole. So the Coriolis effect is less near the equator and greater near the poles. It's almost non-existent at the equator. Okay, so friction, this is just discussing how friction affects wind speed. So what you see there is you see some mountains, maybe that's out in Colorado, and you see that the winds that are close to the surface, well, they're being affected by friction. So they can't flow as easily or smoothly, and they're not going to flow quite as fast. Surface roughness, so as you go higher up in the troposphere, you lose that friction and the winds are going to move faster. So basically, surface friction slows the wind. And we have a question there, lenticular clouds, perhaps, I think in chapter 5. Whatever chapter we did the clouds, I think it was chapter 5. There was a slide with an image of lenticular clouds that look like flying saucers, and they tend to form on the leeward side of mountain ranges, and it's going to have something to do with how friction affects wind speed. Okay, so wind strength increases with altitude, so the snow-covered tree shows the effect of strong winds in a high mountain setting. Where are they? I'm not sure. I kind of wonder if they might be on the top of Mount Washington, Vermont, home of the world's worst weather. Wow. You know, in a hot summer here in North Carolina, I would just love to travel somewhere like that. That would be cold. I guess that probably is in the winter time when this picture is taken. So, some people might put up something called a snow fence. A snow fence is meant to slow the wind and try to not only does it slow the wind and therefore decrease snow's ability to move around, but you could trap the snow on the windward side of the fence. Why would people do this? Well, if you had a big piece of land and maybe you had, cattle and sheep, and you had some interest in not having big snow piles on your land, then you might put up a snow fence. Okay, geostrophic wind, we will read through this briefly, but geostrophic flow, geostrophic wind is not going to be on your exam. Okay, so the only force acting on a stationary particle of air is the pressure gradient force. But once the air begins to accelerate, meaning once you actually produce wind and get some motion going, the Coriolis force will deflect it. It will deflect it to the right in the northern hemisphere. It will deflect it to the left in the southern hemisphere. Okay, so greater wind speeds result in a stronger Coriolis force. Okay, so greater wind speeds, say at a higher altitude, for example. Okay, so greater wind speeds result in a stronger Coriolis force or deflection until the flow is parallel to the isobars. At that point, if that happens, which usually is at a higher altitude, the pressure gradient force and the Coriolis force are in balance, and the flow is referred to as geostrophic flow or geostrophic wind. It's important to note that in the real atmosphere, airflow is continually adjusting for variations in the pressure field. So as a result, adjustment to geostrophic equilibrium is much more irregular than shown. But this is really beyond the scope of our class. This kind of follows up on with that slide we just looked at, again, which will not be on your exam. So an idealized model of geostrophic flow, we're talking airflow aloft or, higher altitudes within the troposphere. We expect that the winds could reach geostrophic flow, where, the pressure gradient force and the Coriolis force are balanced, and you would have flow parallel to the isobars and at a constant speed. And we never really actually achieve that, but it does give meteorologists a useful estimation of winds aloft. Okay, ridge and trough. All right, hang on a second, let me look ahead. Okay, so I have several issues with this textbook, including, well, there's never not going to be an issue, but this is one of them. I kind of think we should discuss cyclones and anticyclones before we discuss ridge and trough. But that's okay, we can reverse it. This is the order in which the slides are presented. In class, I jump around a lot. It's not as easy to jump around in this narrated version. So a ridge is like a high pressure system, an anticyclone, except linear. So ridge makes you think of a mountaintop, so linear high. Okay, and then a trough is a low pressure center. So it's like a cyclone, but instead of being circular, it is also linear. So a trough is like a valley or a linear low. Okay, so ridges and troughs, and I'm not going to ask you about ridges and troughs on your exam, but we won't ignore them. We'll discuss them briefly. So these are upper airflow phenomenon, meaning they're going to occur, where you have an air pressure of 500 millibars or at about 1,800 feet. Okay, so surface high pressure and the fair weather that goes along with high pressure are often ahead of an upper ridge axis. And then low pressure and precipitation are often ahead of an upper trough axis. But we're not going to say much more about ridge and trough because the cyclone and anticyclones are much more important, and we will spend time discussing those. Okay, yeah, this might end up being a 2-hour PowerPoint. Oh well, we got all semester long. So, distinguishing between a ridge and a trough. This image here is actually very useful. So you see there are some isobars, and these are higher levels. All right, these are at higher altitudes in the troposphere, we would say. All right, so, and of course you see those weird hockey stick things, those wind symbols, giving you an idea of the wind speed and the wind direction. So you have a ridge out there in the west, and it actually, in a two-dimensional drawing like this, it looks like a ridge. It looks like the top of a mountain or the top of an anticline. Okay, so the ridge is your elongate high pressure, which tends to be, again, at a higher levels in the troposphere, and then there in the east, like in the Ohio Valley, Mississippi River Valley, you have a trough or a low pressure system that tends to be linear. And it does kind of look like a valley there or a syncline. And then you have that drawing down there in the bottom left, and that drawing is kind of useful as well, which is showing you the location of the ridge and the trough. So at upper air levels, our highs and lows tend to have a linear shape. But again, this is not on your exam. We're going to skip this, not on your exam. Bayes' Ballots Law, we're going to skip this, not on your exam. You are always free anytime you want to pause this video and read through this stuff and then Google it and get some more information, maybe at the NOAA website or the National Weather Service website. And most of what I just said now is on this next slide. Anyway, you can pause this and read about it some more if you would like to. Okay, so what are we looking at here? We'll read through this very quickly. So upper level winds and surface winds, a comparison between upper level wind and surface winds, showing the effects of friction on airflow. So we have A, B, and C. And A at the top, you have an upper level wind with no friction. You have the wind wanting to move in the direction the red arrow goes. You have the Coriolis effect wanting to take it in the opposite direction, deflection to the right, and then you have the blue arrow where the wind actually goes. Okay, so in B we have a surface wind in very smooth terrain, like just grasslands, and then in C we have surface wind with rugged terrain, mountainous areas. So the force of friction is shown in the purple arrow, so you clearly have a greater friction force in diagram C, as you would expect, because you actually have topography there. So friction slows surface wind speed, weakening the Coriolis force, causing the winds to cross the isobars. The pressure gradient force is not affected by wind speed, and thus wins the tug of war against the Coriolis force, causing the winds to blow at an angle across the isobars towards the center of the low pressure. More rugged topography and thus more friction, the more the wind decreases in speed and increases the angle at which the winds blow across the isobars. So again, in blue, that's what the wind actually does, and as they have just described, the more rugged the topography is, you see the wind crossing the isobars there, which are those straight black lines. The wind is crossing the isobar at a greater angle. Do you need to know any of that for your exam? No. But you do need to know that friction affects wind speed, and much more so at our surface, and much more so if you have rugged topography. So we're going to fill in these answers together. The blank makes the wind flow towards the low. The blank deflects it to the right, northern hemisphere, then blank slows it down. The airflow is thus blank around the low when viewed from above. So looking at that image there, we have a low pressure system, a cyclone. Our cyclones are low pressure that are, more circular. You see the isobars there, and then you see in purple the direction that the winds are actually moving. Okay, so what makes the wind flow towards the low? Well, the pressure gradient force. Okay, you have higher pressure on the outside of the circle, lower pressure in the center, and that's going to make the wind flow towards the center. What deflects it to the right here in the northern hemisphere? Well, that, of course, is going to be the Coriolis effect. What's going to slow it down? At the surface, friction. The airflow is thus counterclockwise. So the purple arrows are moving counterclockwise around the low when viewed from above. Okay, so we're looking here. Again, we'll show the United States the vast majority of time on different images in this class. That's what the textbook authors do. It kind of makes sense. They know that that's most of us buying their products are living here in North America or Central America. Okay, so Northern Hemisphere, cyclonic and anticyclonic winds. Meaning, well, we have an anticyclone or high pressure system there on the left. We have a cyclone or low pressure system there on the right. Arrows show the winds blowing inward, converging, and counterclockwise around a low, and outward or diverging and clockwise around a high. So let's look at each of those. Let's start with the anticyclone on the left. H for high, blue for chillier temperatures. You got higher pressure in the center and lower pressure on the outside. So that sets up something we call divergence, which means that the winds are blowing from the high outwards. They're diverging from the high. And our high pressures in the northern hemisphere are rotating in a counterclockwise fashion. So an anticyclone, high pressure system, winds rotate, clockwise. In the high pressure system, the winds rotate clockwise, and that's what you see the red arrows doing there over the anticyclone high pressure system out in the northwest. Now then over there, say in the Ohio Valley, you have your low pressure system, which is a cyclone, also known as a mid-latitude cyclone. That when they are so important, they'll get their own entire chapter. It's a fun chapter. So what's happening here is that the pressure is lowest in the center and higher as you move out in all directions. So the winds are blowing towards the center. So we refer to this as convergence. Winds are converging or blowing towards the center. And what are our red arrows doing? As with all of our cyclones in the northern hemisphere, rotating counterclockwise, just as our tropical storms Laura and Marco are doing right now. Okay, so good question here. All right, we have two images here, and they're both a low pressure system. Well, how do we know that? Well, notice that they appear to be hurricanes. The one on the right is especially well formed, has a well formed eye. So they're both low pressure systems, but they're in different hemispheres. Can we tell which one is which? Okay, so A is in the northern hemisphere. It's rotating counterclockwise. I like to hold my hand in front of the image and physically move it counterclockwise to prove to myself that that's what would make the cloud pattern there. And then the one in B is in the southern hemisphere, and notice that it's shaped different, but that's because it's rotating clockwise. So in the southern hemisphere, our low pressure systems or cyclones are going to rotate opposite. They will rotate clockwise. And these two systems that we're comparing, again, the one on the right in the southern hemisphere is much more well formed and therefore likely more dangerous. Okay, we can skip that. We're going to look at these in more 3D, I think, coming up. Okay, yeah. So this is a pretty good drawing here because now we're not just looking at a two-dimensional map view, but we're going to make it 3D. So just a little bit more differentiation between the cyclone and the anticyclone. Okay, let's start on the west. Your high pressure system, also known as an anticyclone, remember that you have high pressure in the center, so the winds are moving outward from the center. They're diverging, all right, and you see your wind arrows there moving clockwise as we expect. What we haven't talked about yet is that whatever you get at the surface, you'll have the opposite higher up in the troposphere above that cyclone or anticyclone. So if we have diverging winds at the surface with our anticyclone, then at a higher level up, we're going to have convergence. And you see that in the drawing. And that convergence aloft helps to keep the high pressure system going so it doesn't just eradicate itself. Okay, so then over on the right, the low pressure system, shown with a red L, our cyclone, Remember that the winds at the surface, they're converging, as in they're blowing from the outside of the circle towards the center. You see your winds, the blue arrows there, rotating counterclockwise. But whatever you have at the surface, you're going to have the opposite aloft. So higher up in the troposphere, in the cyclone, you actually have divergence. Now notice the clouds that you have higher there, higher up with above the low pressure. And do we expect that? Well, of course we do, because we know that we have rising air that is moist. It's going to cool adiabatically. You're going to have condensation. You're going to form clouds, and you will likely form some precipitation. Generally, we get precipitations with our low pressure systems, our cyclones. Okay, so, and that divergence aloft with the low pressure system helps to keep the surface low going, so it doesn't just eradicate itself. So another thing to point out is back over to the high pressure system on the left. Do you see any clouds at the top? And the answer is no, you don't. You have clear skies. Why? Because it's dense sinking air associated with high pressure. So there's no lifting, so you're not going to get clouds. All right, so a low or cyclone, converging surface winds, rising air giving us cloudy conditions. Our anticyclone or high pressure has diverging surface winds, descending air, which leads to clear skies and fair weather. Okay, you don't have to know this for your exam, but this kind of goes to something I was pointing out on the previous slide, so we'll read through it quickly. Question: for a surface low pressure to exist for an extended period, and they do, they'll go on for many, many days, what condition must exist aloft? There must be divergence aloft. Otherwise, the air molecules rushing in would pile up, which would lead to higher pressure, and it would eradicate itself. So having divergence aloft allows for the convergence surface to keep going and might even exacerbate it and keep it going. And that's why our low pressure system of cyclones will stick around for as long as they do. Okay, question: for a surface high pressure to exist for an extended period of time, what condition must exist aloft? Well, you must have convergence aloft. Otherwise, the air molecules rushing out would cause low pressure, and the high pressure system would eradicate itself. So whatever you have at the surface with your cyclone and anticyclone, convergence or divergence, you're going to have the opposite aloft, helping to keep it going. Okay, so more on that same notion. So other things that are causing convergence and divergence aloft. Am I going to ask you this stuff on the exam? No. I'm not going to need you to know what causes convergence and divergence aloft, but it is worth a discussion. So other examples: as air reaches the leeward side of a mountain, meaning the side away from the wind, or the wind is leaving the mountain, like say the eastern side of the Cascades in Washington State. As air reaches the leeward side of a mountain, the air experiences vertical expansion as it's no longer being compressed. And this is going to cause horizontal convergence aloft. And if it's convergence aloft, it'll be divergence below, and that'll be a high pressure system. All right, an upper level jet stream can also slow down. And if that happens, then you have air molecules piling up. And this is basically convergence aloft, which will help lead to divergence at the surface, which will be an anticyclone. Let me go back and do that first bullet again. No, there's no stopping and rewinding or anything like that when I tape these. You just got to keep going. Okay, so back to the first bullet. As air reaches the leeward side of a mountain, air experiences vertical expansion, is no longer being compressed, causing convergence aloft, which will cause divergence below, and will lead to a cyclone at the surface. So the first bullet will help lead to a cyclone at the surface. The second bullet will help lead to an anticyclone at the surface. All right. High pressure system will develop under the region of maximum convergence aloft. Okay, I take back what I just said. Both of these are two different ways to form an anticyclone at the surface. Both of these things, the air reaching the leeward side of a mountain range or the upper level jet stream slowing down, both of these things will lead to convergence aloft. All right, so higher pressure system developing under the region of maximum convergence aloft. Bottom line is this: convergence and divergence aloft, they are important, but you don't need to know them for your exam. Okay, friction and vertical airflow. Just a little more about this. So when air moves from smooth oceans to land, it encounters more friction because you have more topography, and that's going to slow it down and cause a pileup or convergence. And then air may get carried aloft, and condensation may occur. So this kind of goes back to our discussion of Florida being a peninsula. And remember that in the daytime, you're going to have winds blowing from the ocean to the land. So they're coming in from both directions, from the east, from the Atlantic, from the west, from the Gulf of Mexico, and then converging, making a bottleneck, carrying air aloft, and condensation may occur. When air moves from land topography to smooth oceans, the reduced friction speeds it up, and you're going to get divergence to occur, which will likely lead to subsidence and clearing conditions offshore. Going to skip that. Going to skip that. This is kind of a neat graphic here. So it's reminding us again of some of the differences between the cyclone and anticyclone. And what's cool here is that they've added the appropriate fronts, the warm front on the leading edge and the cold front on the trailing edge of the cyclone, and reminding us that they do have a vertical, that they are vertical features, and that whatever you have at the surface, you're going to have the opposite aloft. Okay, so two different photos here. Is it the same area? It appears to be. Is that London Bridge, perhaps? I'm not really sure where that is. I'm guessing that's London Bridge, or a bridge maybe in the United States meant to look like London Bridge. But you see, these are two very different days. The one on the left, they have the raincoats out, and the skies are all gray with stratus or nimbostratus clouds. And clearly it's raining. And then on the one on the right, you have, wow, clear skies, blue skies, and no clouds. Okay, so which one is high and which one is low? You guessed correctly. The one on the left is low pressure, which tends to bring cloud cover and precipitation. And then the image on the right is a different day when you have high pressure or an anticyclone overhead. Clearing skies, stable air, sinking air, no lifting, therefore no clouds. Okay, how are winds measured? By a wind vane, which has a cup anemometer on it. You do not need to know anything about any meteorological instruments ever on my exams, but we will discuss them. So, okay, the cup anemometer will measure the wind speed, as in the cup catches the wind and it will spin, and of course it will spin faster with faster wind speed, and this gets transmitted into a wind speed in a digital format going to a computer somewhere. And then the wind vane will show the direction while the anemometer is measuring the wind speed. Okay, so this is a weather vane. Look, clearly it's made of brass. You know, look how green it's become as we, or copper, I'm sorry. It could be brass. It could just be copper. Anyway, copper definitely will weather and look like this. So where does a weather vane point? Okay, that's a good question. All right, so the arrow is going to point in the wind direction. So a reminder that winds are named for the direction from which they're coming, not where they're going. Okay, so it's kind of hard to see. It looks like the arrow there is pointing to the west, so then our wind is going to be blowing towards the east, but it will be referred to as a westerly wind. There's a little story there about why You might have the rooster there on the weather vane, especially on churches in Europe and America. You can pause and read about it. Okay, a wind sock is different from a wind vane, all right, or a weather vane. The wind sock, of course, if it's not windy, it's just going to hang there on the pole. But if the wind is blowing, then the wind will fill up the sock. And in the case of the wind sock, it's showing you the direction where the wind is going. Okay, so it's pointing the opposite direction of the wind vane. So if your wind sock is pointing north, it means the wind is flowing to the north, it means it's coming from the south, that we refer to that as a southerly wind. And of course, also you can get an idea of how strong the wind is or how weak the wind is by the shape of the windsock. Yes, it looks like the Cat in the Hat's hat. Chances are that might be at an airport. You know, it's common to have weather instruments at airports. Those are just good places to put them. All right, so what we have here is an aerovane measuring wind speed and direction. Clearly this is at some high altitude location. Maybe this is in the Rockies, possibly, maybe the Canadian Rockies. So this is powered, of course, by the sun. You see the solar panel there. So this is really nice. This is going to give you wind speed and wind direction, and it's going to be powered by the sun and hopefully sending digital data. Okay, so a wind profiler uses radar or sound waves to detect wind speed and direction at various elevations above the ground. Oh, and then the GOES satellites. I think on a previous chapter, they showed us an image from GOES 14. Well, last fall, they launched GOES 16. So we have several of these GOES satellites, and I forget what that geostationary observation Earth satellite maybe. Anyway, these are wonderful satellites that are very useful in meteorology. And of course, every time we put a new one up there, it's more advanced, and we get better and better at being able to, you know, detect how bad a supercell thunderstorm is and where we expect a tornado. We get better at being able to you know, figure out what's going on in a particular tropical storm or hurricane. Okay, so wind roses, this is more of a climate thing than a weather thing, but a wind rose is a diagram basically trying to show the percentage of time airflow is from various directions. Okay, so an A, wind frequency for winter in the United States, and this is pretty high up there. So what is that? That is north of Cape Cod. I don't know, Vermont maybe. Maybe this is Mount Washington, Vermont, home of the world's worst weather. And you see there that for the most part, your winds are coming from the west, the southwest, and the northwest. And the northwest most of the time. And that kind of makes sense because we're in a band of winds known as the westerlies. Okay, now take a look at Australia. Okay, so their winds don't vary as much as ours. So, and this is in their winter, which would be in our summer. But so wherever that is in Australia, your wind flow is predominantly coming from the southeast. Okay, and that makes sense because they are in a band of winds known as the southeast trade winds. And I think it's chapter 7 that we are going to tackle those. And I have a video lesson already filmed from about 4 summers ago for the global wind patterns. But for those of you that make it to class, assuming we're still going to class, we'll do it together in person, and that's more fun. This is the Beaufort scale. Okay, so this is not dealing with hurricanes or tornadoes. Those are different scales for those, the Saffir-Simpson scale and the Fujita scale. But the Beaufort scale has been used for, gosh, dozens of years, many decades, well, probably hundreds of years, because this would have maybe started with, you know, shipping travel. Okay, so the Beaufort scale is a way to describe winds. Again, and we're talking less than hurricane winds. So it goes from 0 to 12, and you have your range of wind speeds there in miles per hour. And then the third column over from the right is what sailors would refer to it as, like a strong breeze or a fresh breeze or a fresh gale or a strong gale, you know, all the way to storm and then hurricane force. So then the fourth column over is trying to show, you know, is the smoke going to go straight up in the air? Is it going to move a little bit? Is your weather vane going to move quickly? Just trying to give an idea in the pictures there of what could happen. So look down there at strong gale, that I think is representing ripping shingles off a roof. Fresh gale is showing that yes, branches can break off. Whole gale is showing trees just snapping. Storm is showing, I don't know what that is. Maybe that's a roof coming off a house. Could be. Anyway, and then the effects on land. 0, calm, smoke rises vertically. Moderate breeze, dust, leaves, and loose paper raised up, small branches move. Fresh breeze, small trees began to sway. Moderate gale, whole trees in motion, resistance felt walking against the wind. Strong gale, slight structural damage, slate blown from roofs. Hope nobody's standing there in the path of that flying slate. Slate is heavy. And then, of course, hurricane force winds, violence, and destruction. And once you hit hurricane, then you're going to transfer over to the Saffir-Simpson scale. And we'll do hurricanes. I think they're chapter 11, the last chapter we did. And then there are flags that can be flown, say in marinas where people either have their boats or they're going to go rent a boat or go on a deep sea fishing expedition, and they'll put these different flags out to warn people. Even a small craft advisory, you've got a small boat, you know, that is not the time to go out on that boat. And then it goes to gale warning, storm warning, and hurricane warning. And then we see the hurricanes. Aren't they Carolina? I think they're Carolina. The Carolina Hurricanes, hockey. So down there on the bottom right, their flag looks very much like a hurricane flag. And of course, that makes perfect sense, doesn't it? Okay, so wind energy. This might be our last topic. Wind energy is going to be important in the future. So if you listen to the naysayers that say, well, solar can't replace everything that fossil fuels do, or wind can't replace everything fossil fuels do, the answer is, yeah, we know that. It's going to take a combination of many things that together will replace what fossil fuels do for us. You know, not to mention the fact that we just can't shit new fossil fuels, okay? If we keep using them at the rate we are, we will run out. So whether people like it or not, at some point we're going to be switching, and we're already switching, and it's a gradual thing. Anyway, wind energy is going to help. Tidal energy is going to help. Solar energy is going to help. We now have solar farms in the Pembroke area. Nuclear. Some people don't like nuclear. I'm a fan of nuclear energy. I think it can be done correctly and safely. And over in France, they do a great job. Anyway, you know, nuclear can help. Hydrogen fuel cells powering cars, and who knows what else we're going to come up with in the future. Okay, so wind energy. So those of you that took my earth science class, if you either came to watch the video together with everybody or you watched it on YouTube and then wrote about it, towards the end they visit, and this is in West Virginia, that documentary takes place, they visit a small private school run by, I think it's run by monks or American monks. Anyway, and they're powering their entire school on wind energy, and I think they only have one windmill there. They may have put up a second one. So, you know, wind power is going to help. And again, nobody's claiming that just wind is going to take over everything from fossil fuel, but we have so many things at our disposal, and together they will take over from fossil fuels. But let's take a look at this. So, looking at the map there, wind energy potential in red is excellent, in orange is good, and in yellow is moderate. I'm going to point out the Appalachian Mountains, my home. And you see there in the Appalachian Mountains, you do have some yellow, orange, and red. You know, kind of makes it mountains. You have faster wind speeds with elevation. Then let's look, say, in the Midwest. There's a lot of areas that are flat, but they're windy, so they have strong potential. And then you can take a look at, say, the Sierra Nevada mountain range in eastern California, the Cascades and Coast Ranges there in Northern California, Oregon, Washington, the Rockies there. Anyway, there are definitely places where wind is going to be useful and viable. Wind is free, available in many places. China utilizes winds that are around 13 miles per hour. 36 U.S. states now have windmills, including West Virginia. So the red, where it says excellent, are showing wind speeds of 7.5 meters per second and higher, or greater than 13 miles per hour. The orange is going to show 7 to 7.4 meters per second, and the yellow is going to show 6.4 to 6.9 meters per second.